So this is the problem we stopped in the previous class. We're just continuing from this. Given is 300 kilonewton meter. So what do you need to find is the diameter. So let's continue. So bending moment. So MB is the bending moment, is given as I think 200. Yes, 200, not 300. It's 200. Again the same thing, kilonewton meter. And this also will be converted into Newton mm. Let's try 10 power 6 Newton mm, right? And now let's write the governing equations, okay, which are required to find these values here. So number one is maximum shear stress theory. Okay, so as we saw in the PPT, these equations, the theories of failure, are not given for static stresses. So I have looked at the data handbook, and it is not quite given. So maybe you need to memorize this in some way or the other to extract the value. So number one is maximum shear stress theory. Shear stress theory. So according to maximum shear stress theory for a 2D body, tau max is given as sigma 1 minus sigma 2. Sigma 1 minus sigma 2 by 2. Okay, this you need to memorize. Right. So this is our equation for according to the maximum shear stress theory. This tau max given as sigma 1 minus sigma 2 by 2, where sigma 1 and sigma 2 are nothing but principal stresses. Okay, so we have defined that before. And second one is distortion energy theory. Let's say distortion energy theory. Distortion energy theory. So distortion energy theory, the equation again is oblivious to us. So what we can surely say is it forms an ellipse. We have seen that before. It forms an equation of ellipse. So again, I think you need to memorize this also, because these are very basic and elementary equations. So better you memorize this. Square root of sigma y over factor of safety is equal to equation of ellipse, that is sigma 1 square plus sigma 2 square minus sigma 1 minus into sigma 2. So this is the equation of ellipse, sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So where sigma 1 and sigma 2 again are principal stresses. So sigma 1 sigma 2 values are principal stresses, the governing equation. So this also is important with respect to your career in interviews. Many times the questioner asks the interviewer asks that uh, give the equation for von Mises or distortion energy. This is also von Mises. Okay, most commonly used, as I told, von Mises or distortion energy Henke theory of failure. Okay, so this is very important. So I hope you by heart this. And third one is what we have asked in the question. We are not doing this. So maximum principal stress theory or normal stress theory. So we'll say maximum normal, or it's also called principal stress theory. So principal stress theory you already studied, right? So this one it is also available in the data handbook. So what we can say is this sigma 1 comma 2 is equal to sigma by 2 minus plus or minus square root of, this is for a 2D body which is subjected only axial stress in one side and also shear, sigma by 2 the whole square plus tau xy square. Okay, this is also available in the data handbook. You can look it up. Only thing I have removed is sigma x minus sigma y. Sigma y I am entirely removed. Why? Because you see there are only two loading conditions acted here. There is MT and MB. So these two loading conditions. So what they'll give us is just it gave MT. MT is torsional moment. Torsional moment gives us shear stress, whereas bending moment gives us the normal stress or sigma. Okay, so that's why I've condensed this equation into only sigma and tau. So also don't need to write xy here because you're getting only shear stress tau. So according to the importance, we need sigma 1, sigma 2 first, right? So what we'll do, we'll first start applying this, finding out the value of the maximum, normal and principal, normal or principal stress theory, that is maximum and minimum. Later on, whatever values you get, we'll just fill in the previous two theories of failure and find out what will be the diameter according to those values, right? So let's start off. We'll start off with, maybe this finding out these. So here again, sigma and tau are unknown. Okay, so see, we don't know sigma and also we don't know tau, the value of tau, to find using this maximum principal stress. What do? We find sigma and tau using the traditional equations. Okay, so let's find sigma first. Sigma is nothing but here, since the component is subjected to bending stress, you say it is bending. It is bending stress, which is nothing but sigma. So that is bending moment MB by I, moment of inertia, into C. Okay, so this equation also I think you are familiar with. You have used multiple times so far, where I is the moment of inertia for circular cross section. Okay, for circular cross section, you need to refer to the data handbook, as I told you before. I'll show you the data handbook. Close. Oh, somewhere here. This is one a little bit far. Bending. I think I probably what tables. A similar table like this. So let's say here in table 2.7 for circular cross section, what is the moment of inertia I? So moment of inertia I is given as pi d power 4 by 60. So this value we need to plug into the equation. So pi I is pi d power 4 by 64. Similarly, C is d by 2. So let's write that here. So sigma is I is MB. Bending moment already given 300 into 10 power 6 by 5 d power 4 by 64 into d by 2. Okay, so what we'll do, we'll cancel this d cube, so this will be as 300 into 10 power 6 by pi d cube into, you get like 64 by 2. Okay, so once you reduce this equation here, right? So once we simplify this, we'll get in terms of d cube. Let's see you guys simplify this equation here, and we'll get sigma. So this will be sigma, which will be in terms of d cube. Okay. Next will be shear stress. We need to find the value of shear stress, right? Shear stress tau is, so here it is subject to torque, right? So we'll write it in terms of torque. So mt by j into r. Okay, this is the equation, mt by j into r, where j is your polar moment of inertia. So j is, for this again we can go back to the data handbook. Again, j, I think it's not in terms of j here, it's like this polar section modulus, j by c. So we can write this, so this is c, not r. So c and r doesn't make any difference, much difference here. So this we can write it as mt by z. So where z is equal to, for a circular cross section, you can check here. So it is pi d by 16. You see pi d cube by 16. So let's just continue that here. Mt is 200 into 10 power 6 over pi d cube, again divided by 60. Okay, so this will give us our shear stress, again, which is in terms of d cube. Okay. So before we proceed, let's calculate these values first. If you calculate, you can post the values in the group chat. So let me calculate this. It is 306 64 divided by pi into 2. Okay, so I'm getting value. Correct. You're right. So this is the bending moment. This is around. Let me copy our value here. We got 3055.7 into 10 power 6. Okay, so that is our stress, is in terms of d cube. And now about shear stress, that is tau is 200 E6 times 16 over 5. E6 over 5 into 16. So here we have a value like 1, 0, 1, 0, 1, 8.5, 9 into 10 power 6. Right. So you got these two values. Let's so now that we have sigma and tau, we need sigma and tau for us to find the principal stresses using the principal stress theory. So we'll use this here and we'll find out what is the stresses or the maximum and minimum principal stresses, and in turn the dimensions later on. Okay, so let's do that. So this is the equation we need to plug these values into. Let's start off one by one. Okay, so sigma 1 is sigma stress value. So let's take off this here. Let's copy this value. Okay, so this by 2 means you have this 2 dq plus or minus this is sigma 1, so let's put only plus. So plus square root of again this entire value whole square. We get a big equation here. So this whole square plus again you have 2 over here under the root. Tau is this value over here. Just copy this. Okay, so this square again whole square of this whole square. Right. So we have a really big equation. Let's try to put this in order now. So just for sigma 1, let us consolidate. So this is equal to what we can divide this by 2 first off. So it's 3055.7 E6 divided by 2. So get like half of that. Three zero five five point 7 E6 divided by 2. Just find out the value until then. 3055.7 E6 over 2. We're getting somewhere. So let's write it as 1.528 into 10 power 9 over d cube plus, so let's simplify both of them maybe at a time. Try that. So 3055.76 square divided by 4 plus you have 2 into 4 into 101, 101, 8.59 E6 squared. Square root of that. Divided by 2. So I'm getting a value of 1.273 into 10 power 9 over d cube. So once I consolidate this, plus we get 1.528 E9. Get a value like 2.8 into 10 power 9 over d cube. So you can just verify. I think done a little bit quick in my calculator. You can verify this at your own pace, and this will be the sigma 1 value. Similarly, sigma 2 will be minus of this. So just the same thing will be negative. So if you do that and plug it here, let me see what you get. You get 1.528 E9 minus 1.273 E9. So you will get like 2. You get 0. This is power 9. The conclusive store 4. This is 9. So you get 0.255 into 10 power 9 over d cube. So you see, by contrast, this here is we are getting a bigger value here. So this we take it for consideration. Okay, you take this for consideration here. That is sigma 1 value here this will be taken as consideration. That is a maximum principal stress. Similarly, this is minimum, right? So we'll ignore this. Okay, now for maximum principal stress theory, so it states applying, let's say, applying maximum principal stress theory, max principal stress theory. So what happens here now? Maximum principal stress theory states that it's sigma 1 equal to this sigma y yield by factor of FOS. Okay, you see here we have the yield stress value. Yield stress value 353 megapascal, nothing but Newton per mm square. So our maximum principal stress theory states that we should not exceed this value. That is the yield, again divided by factor of safety. So it should not exceed this. So if you exceed, which means that it's a failure. Okay. Sigma 1 value now we have found out to be 2.8 into 10 power 9 by d cube. This is equal to sigma y. Sigma y is 353 Newton per mm square by factor of safety. I think it was given in the data. Factor of safety you take as 3. Again, this is a standard value, standard equation. Okay, so with this we'll get what is the value of the diameter T. Okay, so what is diameter according to maximum principal stress theory? We'll get one value here. Similarly, we'll replicate this for the other two theories of failure under consideration. So let's see the other two considerations. Now that we have sigma 1 and sigma 2, we can find that, right? Let's do that. So 2.8 E9 into 3 and 353 divided by the answer divided by 353, then cube root of that is giving us a value like it's 287.63. So this is our diameter considering uh, you know the principal stress theory. Okay, so let's find out using the other two theories of failure. Okay, so let's find out this maximum shear stress theory. So maximum shear stress theory given by Tomax. This equation here, sigma 1 minus sigma 2 by 2. Let's find out using that. Now we have found using the maximum principal stress theory, that is the third one. So this was done just because we needed sigma 1 and sigma 2. So now we have these two values. Let's find out. So tau max is sigma 1 and sigma 2. Again here, sigma 1 sigma tau max is it contains another hidden formula. So tau max is also written as, according to maximum shear stress theory, we saw it was 50%. That is 0.577 times the yield stress. 0.577 times the yield stress divided by factor of safety. Okay, this again is a standard value, which is I showed you this in the presentation also. Maximum shear stress is calculated as 0.577 times sigma y of factor of safety, or you can also say that you can say sigma y by 2 into factor of safety. You can also consider this as half of yield stress over factor of safety. You can consider similar to that, right? So let's do that using this equation here. So sigma y, we knew it on the LHS. I'm writing the LHS now. So sigma y was 353 divided by 2 into factor of safety was 3. Okay, so that is equal to sigma 1. Now sigma 1, don't just plug in this diameter and find out. So you need to take this value here, 2.8 into 10 power 9 by d cube. That is sigma 1. So we are finding the diameter according to various theories of failure, right? So that's what we need to do here. So let's write this 2.8 into 10 power 9 divided by d cube. So 2.8 into 10 power 9 by d cube minus, now sigma 1. Sigma 1 was 0.255. Same thing. So this is 0.255 into 10 power 9 divided by d cube. Again, this whole thing divided by 2. Sorry, you could have done just half of this whole thing, 1 by 2. So in the next step, this half goes over to that side, and now 2 gets divided. So let's see how that happens. You see here 2 into 3, 5, 3 by 2 into 3 is equal to, so now we can subtract this, right? So subtracting this, you get 2.8 E9 minus 0.255 E9. So you get in subtraction the value like 2.545 into 10 power 9 by d cube. So your 2 gets cancelled, and we can simplify this, just a single step in the calculator. We can find what is the diameter according to maximum shear stress theory. Let's do that. This into 3 divided by 353 and cube root of that. So diameter according to shear stress theory, you're getting 278.62 mm. So you can check this answer. You can check this answer and find out for your own. And one last thing, according to distortion energy theory. Again, I told you this is very important with respect to your jobs and stuff. Okay, so the last one is von Mises stress. Yeah, you're right with the diameter. The last thing, again, you need to find the diameter using von Mises stress. So this is the second answer. Second answer, diameter according to maximum shear stress theory. So you can see it is different. Considering various theories of failure, you get different values for each. So this also, I strongly recommend you by heart the value, because many times it gets repeated, and also it is important from your career point of view. The distortion of von Mises theory of failure. Right. Let's continue. Sigma y by factor of safety, or n the whole square. LHS we already know. Sigma, the RHS also we already know. Let's just plug the values. So sigma y is 3 change. This is 353 by 3 the whole square. Factor of safety was 3 is equal to sigma 1 2.8 into 10 power 9. 10 power 9 by d cube the whole square plus the sigma 2 was 0. I think 255, right? 0.255 into 10 power 9 divided by d cube, again the whole square, minus both of these. This is 2.8 into 10 power 9, again into 0.255 into 10 power 9 whole divided by d cube. This will become like 6 again. So d cube and d power 6. So let's see how we can find this out. Let's simplify this. So I have 353 divided by 3 and square of that. So you have LHS 13845.44. So this is equal to, when you square that, you have I think you get in terms of d power 6 itself. So 2.8 E9 square plus 0.255 or 9 square minus 2.8 2.89 into 0.255 E9. So this value divided by 13845.44 and the 6th root of this value. Right. So Let me find out RHS here. So you can, what you can do, you can put this value squared plus this value squared minus this multiply bracket for inside brackets. You can enclose all of this. So you'll get a big value like you get 7.19 into 10 power 18 whole divided by d power 6. So once you do all of this, right, you get a value like 7.19 into 10 power 18. This is 1818 over d power 6. So plug this into the equation and diameter, you get a value by doing your calculator as 283.52 mm. Okay, that's our last value for the diameter. So you can summarize right now. So we did 3 theories. That is, first one, according to Mach's principal stress. Mach's principal stress theory, we got diameter as 287.63, 287.63, and second one we did was maximum shear stress theory. Shear stress theory. According to this theory, we got diameter as 278.62. 278.62 collar in mm. And according to the last one, that is von Mises or distortion energy theory. Distortion energy theory. According to that, the last value we got as 283.5. So you see, comparing these values, you can clearly see that you can say maximum principal stress was very liberal. So this gives more dimensions. So more dimensions means more weight, more mass, and more energy is required to move this particular shaft, right? Cylindrical shaft. Whereas the maximum shear stress theory is stringent, very strict. Whereas distortion von Mises theory is just right, so just perfect. So that's why most of the times in practice we use distortion energy theory. It gives somehow an optimal balance between the values, okay, obtained. So that's why most of the time it is considered as to use this von Mises stress, okay, because most accepted theory of failure kind of a thing, right?